So let's look at a few issues involved with bond vibrations in IR spectroscopy. So this is what we're going to talk about today. We're going to talk about the nature of how electronic effects change vibrational frequencies, mostly by looking at how hybridization affects the frequency of a CH bond. We're going to look at how changes in force constants and the mass of the atoms involved changes vibrational frequency. We're going to talk about how conjugation and hydrogen bonds can change the expected observations of absorption peaks. And of course, we're going to talk about peaks that often don't show up at all or show up very weakly due to weak dipole moments or symmetry in the molecule. So let's start off with sort of typical CH vibrations. Here we have some basic alkane stretches, and we have already calculated that alkane stretches come out at around 3,000 centimeters per centimeter. And so we expect them around 3,000 per centimeter, and that's where we see them. You can see all of the alkane stretches in this molecule. There's 20 CH stretches in this molecule, and they all add up to 3,000. Remember how to calculate that? If we know the force constant, which we estimated to be 5 times 10 to the 5 dynes per centimeter, and we know the formula for calculating frequency that we discussed earlier, we can calculate that the frequency of vibration of a CH bond should be about 3,000 per centimeter. And in fact, that's what we have. So that's a CH bond in an sp3 hybridized alkane, a very boring molecule. All 20 of those combine to create that little forest of stretches between 2850 and 2950 per centimeter. There's 20 different, well, I shouldn't say there's 20 different frequencies there. There are many different frequencies envisioned there. Symmetrical frequencies do not show up, but any asymmetrical stretches or stretches that involve in a change in the dipole moment are going to show up, and they're all around that frequency, and they all combine to create that complicated signal for the CH stretches. Other frequencies that we see in IR typically are the bending frequencies. These have lower force constants, same masses involved, but the force constant for bending is a lot easier. And if you think about it, if you get on one of those little children's rides you see in a park that are based on a car spring, it's easy to bend that thing side to side and wong around on it. But if you try to jump up and down on it, it doesn't move very much because the force constant for stretching and compressing that spring, a car spring, is far greater than the force constant for bending a car spring. So here we see the bending vibrations are in fact at lower frequencies, as expected. Now, stretching in alkenes is a little different. You can see that we have the CH stretches there just below 3,000, but just above 3,000 we have that little peak there on the left-hand side of the CH stretches. That's the alkene CH peak. The first thing I do when I look at a IR spectrum is I draw a line right down 3,000. And anything to the right of that line, those are your CH peaks for sp3 hybridized atoms. Anything to the left of that line is likely sp2 or sp hybridized CH stretching. And so if you see any detail, any fine peaks, or certainly large peaks, to the left of 3,000, you have a strong reason to suspect that you're looking at alkene CH stretches. Now in this particular molecule, we see the observed CH stretch is at 3090 per centimeter, so that's higher than 3,000. So anything higher than 3,000 would be your planar or linear CH stretching systems. Of course, there's the bending stretches that we would expect to see, and the alkene carbon-carbon double bond stretch that we calculated would come out in the neighborhood of 1650, and there it is at 1645. Notice on the right-hand side there the alkene CH out-of-plane bending. We see, of course, the alkyl CH2 and CH3 bending, and then we see some new peaks due to the alkene out-of-plane bending. And if you're bending out of the plane, if you're bending up and down in an sp2 system, there's really no atoms above or below to crash into, so it's an even lower force constant, and that's why we see those bending frequencies down there. Now, linear systems, sp hybridized systems, have an even higher stretching frequency. Look, it's not 3090 there. There we see it at 3320 per centimeter. That's a lot higher. The force constant for an sp-CH bond is a lot higher than the force constant for an sp2 hybridized bond, which is significantly higher than that for an sp. We see the usual bending vibrations. We see the alkyne carbon-carbon triple bond peak there at 2130, and notice how much higher that is than the 1645 for the double bond peak. And that's expected because, of course, it has a higher force constant and with the same masses of atoms. The alkyne CH out of plane bending is far to the right-hand side in the spectrum there, because you can imagine that it's even floppier to flop off the end of to bend off the end of a linear system than even a planar system. So there's really nothing around there for it to crash into, so it's a pretty easy bend. Now, that frequency, what sort of trends can we expect? If we expect to see CH stretches around 30 per centimeter, what do we observe? We see, as you can see from this table here, that alkanes come out just under that, alkenes, CH stretches come out just over that, and alkynes are a lot higher. What does that correlate with? It seems to correlate with bond length. Shorter bonds seem to have higher force constants. That seems to be a trend. It seems to correlate with hybridization. The greater S character in your bond, the lower or the higher the frequency of vibration. And it seems to have a correlation with pKa, or the acid dissociation constant for that proton leaving and leaving behind a negatively charged carbon. And that would relate entirely to the ability of that carbon to stabilize that negative charge. And you can see that carbons that can stabilize a negative charge in a lone pair, like an alkyne, have a much lower pKa and therefore are much more acidic, more likely to give up that proton than, say, an alkane. Now, all of this seems to relate to the S character. S orbitals have a much greater connection to the positive charges in a nucleus than p orbitals, which have a node at the nucleus. So the more S character that you have in a orbital, the greater contribution of the positive charge of the nucleus to stabilizing those electrons. This leads to the orbital being tighter, which means, of course, you're going to have a shorter bond length. Tighter orbitals are going to give tighter bonds. And, of course, orbitals that have more connection to the positive charges in the nucleus are going to stabilize a negative charge in the lone pair better. So it seems that SP, more S character, leads to higher frequencies, and that's why we see higher frequencies with SP characterized or SP hybridized alkyne systems. So they're really easy to spot. So here's some key observations. Basically, draw your line down 3000. Anything just to the right is SP3. Anything that's higher in frequency is SP2, and if it's a lot higher in frequency, it's SP. So those are some notes that we might expect from carbon-hydrogen vibrations. Now let's talk about what happens when we change force constants. Let's take two atoms that are the same mass, like two carbons, and change the force constant between it being a single bond and double bond and a triple bond. Here we expect to see a single bond come out for a carbon-carbon bond. We can calculate that, and we expect to see it around 1200 per centimeter, but we don't see anything there. And why is that? Well, a single carbon-carbon bond's very similar at each end there. Just two carbons, they've got the exact same electronegativity, very similar mass overall at either end. It's going to give you a very weak signal in IR. We'll talk about that later, but basically bonds that don't have a dipole or can't generate one as they stretch won't have a changing dipole in their vibration and therefore are invisible in the IR. You need a changing dipole to be visible in the IR. Now the alkene stretch, we expect it calculated to be at 1680, and we get it at 1645, and that's exactly, within spec there, it's what we expect to see. Notice it's weak. Now that's because we have two carbons there, and two carbons are not a lot of difference in polarity, and so that's a weak dipole. The two ends of that alkene are different. One's a CH2, one's a CH connected to a carbon, so it's asymmetric. We will see a vibration likely, but it's weaker because we don't have a strong dipole. But there's enough of a dipole to see. The alkyne, of course, we would expect to see it by calculation with our estimated force constant to be around 2060, and there we see it up at 2130 per centimeter. And that's pretty close, considering that we're just ballparking these force constants. It's weak as well because there's not a lot of polarity there, but there is enough to see. Now, if that alkyne was symmetrically substituted, carbons at both ends of it, it would be almost invisible or completely invisible. Now let's look at some highly polar bonds. Here we're looking at a highly polar carbon-oxygen bond and a highly polar carbon-chlorine bond. What would the effect of mass have on a vibration? Well, carbon-oxygen bonds come out around 1100 per centimeter. And there we see it, right there at 1160. And they tend to be really intense because obviously a carbon-oxygen bond is going to have a very strong dipole. And you notice the whole fingerprint region of the spectrum there, that busy region between 1500 and 800 that's usually quite busy and difficult to interpret. It all seems amped up, and that's because the polar bonds in this molecule all their vibrations are coupling with other vibrations, which might normally be a little weaker, and sort of creating polarity throughout the whole molecule, and so all the vibrations seem stronger. Now, a carbon-chlorine bond we would calculate to be coming out at 975 because it's a more massive molecule, and if we have the same force constant, we expect it to come out at 975. But we see two CCl stretches, and they're significantly lower at 670 and 755. Now, they're lower because the carbon-chlorine bond actually has a significantly lower force constant than a carbon-oxygen bond. It's a much bigger element. It's a different nature of a bond than a carbon-oxygen bond, and as a result, it's got a weaker force constant. So not only were we changing mass, we were changing force constants here, so our calculations failed. Didn't give us the right frequency. So not every single bond has a force constant of 5 times 10 to the 5 dynes per centimeter, which is what we use. These are floppier bonds. If you look at the bond length in carbon-chlorine, it's a lot longer than a bond length that you would see in carbon-oxygen. So it's longer and floppier. That's really why it's lower. But there's 2 peaks. That's a mystery. There's only one carbon-chlorine bond, and I see 2 peaks that are associated with it. The reason is that what we're looking at here, outside of those 2 peaks, is the fact that there are in fact 2 different molecules giving those 2 peaks. I shouldn't say molecules, I should say 2 different shapes or conformations. So we had calculated the force constant, we calculated the original frequency using the force constant. We got 2 different numbers because in fact the force constants are lower, but I seem to see 2 different force constants here. Why is that? It's because there are 2 stable conformations for this chlorine carbon bond. One, you see on the far right there, the most stable one in this graph, is 180 degrees from the oxygen, and that puts it dead center between the 2 hydrogens that are on the carbon that has the oxygen, and basically that is our most stable, farthest away from other atoms conformation. Now you could go to what's called a gauche conformation, where we turn around and the next most stable one, we go over to where we've got, if we follow from the left there, from 180 degrees, so we follow from the right-hand side, my mistake, from 180 degrees, and you go through 170, 160, all the way up there to around 130, we see the worst energy so far, and that's because that chlorine is directly opposite a hydrogen, and we're getting clash. And then if we can slip it in between the hydrogen and the oxygen, there at around 75 degrees from the oxygen, we have found another little area of stability. And then, of course, we could go all the way up to 0 there at the left, and where we're opposite the oxygen, 2 large molecules. Well, the carbon-chlorine, of course, is quite large. The oxygen's got a lot of electron density, and the electrons hate each other. Remember, they hate each other, so that's a pretty high energy situation. But the 2 lowest energy situations are not very far apart in energy, and so at room temperature, there'd be a lot of each. And since there's a lot of each, we're actually seeing IR as an instantaneous spectroscopic technique. We see what's there. Flash! We saw both. And so we see actually 2 signals because we're actually looking at the 2 populations. There's a certain amount of the most stable and a certain amount of the less stable, but they're very close in energy, so there's just lots at room temperature. Mass has a significant effect. Here's hexane, and compared to the IR spectrum of deuterated hexane, where every single hydrogen atom has been replaced by a deuterium atom, which is just hydrogen, but it has an extra neutron. It weighs twice as much. And look what doubling the mass does to the spectrum. I invite you to use Hooke's law to calculate the frequencies with deuterium and see if they come out close to the frequencies that we observe in this spectrum. Remember, we calculated the CH stretches there for hexane. We calculated the CH stretches, and we saw that they were around 3,000. Can you get a similar number for the CD stretches in deuterated hexane? And the same for the bending. Can you see how much it changes? So I challenge you to do that math and see if you get the results. But you can see the effect of changing mass when we don't change the force constant, or at least not very much. So try it out at home. So the key observation here is that force constant affects the frequency. Obviously the carbon-chlorine force constant was a lot lower, and therefore the frequencies were a lot lower. And increasing mass changes the frequency. So going from carbon-hydrogen to carbon-deuterium reduced the frequency quite a bit. So those are sort of some thoughts about force constant and mass in vibrations. Now, of course, you can have a bond, like a carbonyl bond, and its frequency can change based on its neighbors. Conjugation can weaken the force constant of a carbonyl group. Now, carbonyl groups are very strong signals. You can imagine they're very polar, and you can see that in very strong stretch around 17, 15 centimeters or per centimeter for just an ordinary unconjugated carbonyl there. So we expect to see unconjugated carbonyl peaks around 710. In this particular molecule, it is observed to be 1713. So that's pretty typical for an unconjugated ketone, just a boring ketone. We of course see I drew the line down 3000 there. We see peaks to the right of that line because we see alkane peaks, and we know that they're alkane CH stretching, but I see peaks to the left of that line. And why? Because of course there's alkene groups in there. A benzene ring is really a circle of alkene groups. So, and you can see the carbon-carbon double bond stretching. It's kind of weak, but you can see it in that alkene for the benzene ring as well, just to the right of the carbonyl peak. Now, if I take that carbon out that's between the phenyl ring and the carbonyl so that they're conjugated, look, observe that the peak now is lower in frequency. We went from just above 1710, which had 1713, to just below it. That carbonyl group now has a lower force constant because it is conjugated to a distributed pi system. As always, throughout this lecture, I just want to remind you, I'm not using the names of these molecules because I want you to name them. You have to be able to name these molecules. These are simple, straightforward molecules. You learned the rules of the nomenclature last year. Try it out. Try and name these molecules. If you're having trouble, ask me a question. So an ordinary ketone we expect in the neighborhood of 710, and there it is. But a conjugated ketone is lower. So if we've got a ketone and it's lower than we expect, we might expect that it is conjugated. And why is that? Well, look at these two pictures. I could draw the ketone with its bonds in a local format, or I can draw them as sort of a distributed format. And where all the molecular orbital spans 4 atoms there, because there's 4 sp2 atoms in a row. And all 4 p orbitals are lined up parallel to each other, so they all 4 are talking to each other. It's not 2 separate pi bonds. It's 4 p orbitals making 4 molecular orbitals that represent those 2 pi bonds. Now, the carbon-oxygen bond in a ketone it should be 2, right? 2 bonds. But you can calculate that its bond order is actually 1.8. And that's because some of that bond density, some of that pi bond density is in the single bond, what you would think is a single bond between the two. That bond is difficult to rotate. The system is generally planar and locked in that planar formation, because to rotate you would have to break the distributed system and go to 2 separate pi systems, which is higher in energy. So you can actually calculate this using an empirical computational technique called Huckel molecular orbital theory, and get the bond order for each of those bonds. And you'll see the double bonds are a little lower than 2, and that single bond is a little higher than 1. Anyway, if your bond order is a little less than what it should be, your force constant is probably a little less than it should be. And that is why the frequency is lower. So let's look at some examples here. You can see that the ketone that was not conjugated is in fact higher than the ketone that was conjugated. Now, oxygen-hydrogen peaks, that's a pretty tight bond. Oxygen is very electronegative. Hydrogen lets a lot of its electrons lean toward the oxygen. So you not only have a covalent bond between them, you also have dipolar attraction. As a result, an oxygen-hydrogen bond is stronger, or at least has a higher force constant, than a carbon-hydrogen bond. And you can see it there at 3,600 per centimeter. So that's a lot higher than 3,000, isn't it? So there, an oxygen-hydrogen stretch has a much higher force constant than a carbon-hydrogen stretch. So that's why it's way up there. So if we have this cyclohexanol in dilute solution, so they're not running into other cyclohexanols, and this is in a chloroform solution, and that's why you can see some breaks in the spectrum. Those are regions where the chloroform itself absorbs, and obviously if the solvent absorbs, it's just going to be dark. So you get nothing but noise in those frequencies, and they've been cut out. So their alcohol OH stretches at 3,600. But if we did this in a neat solution, so we'll just go by these notes. So if we did this in a neat solution, a neat liquid solution, all of those oxygen-hydrogen bonds can talk to each other. Basically, you would have hydrogen bonding, just like water is hydrogen bonded together, and that's why water is a liquid at 25 degrees rather than a gas, as you might expect it would be otherwise. Alcohols can hydrogen bond to other alcohols, and oxygen alcohols can hydrogen bond to any water that's in there as well. This hydrogen bonding network, you can imagine, weakens the force constant because some of the electrons in the oxygen are now talking to the hydrogen. The hydrogen takes a very, very tiny move toward the oxygen that it's starting to make a hydrogen bond with. You weaken the bond because remember, to make a hydrogen bond, you're going to get overlap with the anti-bonding orbital of the OH bond. And that lowers the energy of the lone pair of the OH in the alcohol and results in an overall lower energy situation in general, which is why hydrogen bonds form. Hydrogen bonds don't just form one way. Obviously, you just look at the diagram on the right there. They could form like multiple ways. There's all kinds of ways to make hydrogen bonds. And as a result, you get not only a lower frequency, but a great big blurring. There's not just one way to hydrogen bond. There's a billion ways to hydrogen bond. They're all slightly different. And so rather than one sharp peak, we have a whole bunch of peaks lined up beside each other, and you get this blurred, broad peak. And those are just three examples of how hydrogen bonding might occur. You can see they involve different angles, different approaches, different positions, and so that's why we have that blurring. So basically, conjugation can change the bond order, and that might result in a slightly lower frequency, or sometimes a slightly higher frequency if that conjugation is in fact interfering with some other more stabilizing force, as we'll see in vinyl groups attached, vinyl esters in carbonyl groups. And hydrogen bonds can result in the broadening of a peak. And of course, when you actually take an IR for real, no matter what it is, you will see that massive water peak around 3300 where we saw the alcohol peak, blotting out everything there like the sun. So unless you make a lot of efforts to keep your samples dry, you're going to see the result of hydrogen bonding due to water impurities. So those are some things that can affect your peaks. Conjugation can change their frequency slightly, and this is useful in characterizing carbonyl systems. Is it an ester? Is it an aldehyde? Is it an amide? We can kind of get a sense of that by the exact stretching frequency of the CO peak. And hydrogen bonding can lead to broad peaks, especially down around 3300, whether it's a carboxylic acid, an alcohol, and of course water is always there to add its signal in a sort of a basic spectrum. You're going to see these broad peaks down there around 3300 per centimeter if you've got any kind of OH functionalities there at all. So if you see that, you go alcohol. Amides also have peaks in that area, and you'll see those examples in class. Sometimes a peak doesn't show up. Why is that? Well, you've got to have a dipole to have a peak. A carbon-hydrogen bond has a dipole, and so you can expect that you're going to see nice strong peaks with carbon hydrogens. It's not the world's strongest dipole, but it is significant, and therefore we see a nice signal. The carbon-carbon bonds, though, have no dipole. So you can see a dipole in CH because of the different electronegativities, and we see lots of nice signals from the CH, whether bending or stretching. But we don't see a peak for carbon-carbon. Why? Its dipole is very small, and just obviously if it's in the center of the molecule, it almost doesn't exist because both carbons are very similar, one carbon attached to a lot of others. Toward the ends of the molecules, there is some small differences, but they just don't add up enough to make those two carbons different enough. However, if you do have a molecule with lots of dipoles in it, you're going to see lots of signals. Here we have an alkyne, but it's attached to a carbonyl group, which is going to put a lot of polarity into that alkyne. And look how strong the alkyne signal is once we've added polarity to that group. We see the carbon-oxygen bonds. There'll be one from the carbon to the oxygen from the carbonyl and one from the ethyl carbon to the oxygen. And so you see the CO stretch there. That's actually two signals, so it looks a little broader. There's the carbonyl stretch. It's an ester. So it should be a little higher, like around 1730. But of course, it's conjugated to the alkyne system, so that pulls it back down to about 1710. Then we see the sp3 orbitals and the sp-CH stretch. Notice how weak the sp3-CH stretches are. They're not weak. It's just that all the other peaks now are so strong that, of course, when you set the scale on your spectrometer, you're trying to get them on scale, and we lower everything, and so the CH peaks seem weaker relative to the huge tower of the carbonyl and CO stretches. That's just they're relatively weaker. Can you name that molecule? Give it a try. So if a stretch is symmetrical, it will tend to vanish in the IR. Let's look at this terminal alkyne. Very easy to see. we have the strong CH, SP hybridized CH stretch, and we see, of course, the carbon-carbon triple bond stretch, the SP hybridized alkyne stretch, and a very characteristic signal is the CH bending in alkynes. All of these are very easy to spot for a terminal CC triple bond. But if that is in the middle of the molecule, it vanishes. The CH stretch is no longer there because, of course, we've substituted it with a carbon, so you don't expect to see a CH stretch. There is no CH off that alkyne. But the carbon-carbon triple bond stretch itself disappeared because this molecule is perfectly symmetrical. And even if the molecule is what you might call pseudo-symmetrical, where the molecule is not symmetrical, but we do have similar groups at either end of that alkyne, don't we? I have a carbon off of one end of it, and I have a carbon off of the other end of it. And even though that molecule is different, they're similar enough because I basically am using the same words. I am a carbon attached to a carbon at one end. I am a carbon attached to a carbon at the other end. I just use the same words. So the signal is, it's not gone. I think you can kind of see it. I see a little tick that might be it, but it's very weak. And if you have a noisy spectrum, you're not going to see it at all. And that's because the molecule is symmetrical enough, or pseudo-symmetrical. If you want to see peaks that don't show up in the IR, there is an IR technique that will do that. We're not covering this in our course, but Raman spectroscopy is sort of I would call it IR fluorescence, if you will. It's actually a dynamic scattering technique where light is absorbed from IR. You get an elevation in the energy level, and then as that relaxes down to its original position, it will obviously give off that light in any direction, a bit like fluorescence. Anyway, what you can see in Raman IR spectrum is polarizability moments, which are different than the moments that we see in regular IR. So it's not just whether or not you have a different electronegativity difference and we have a dipole moment. IR sees dipole moments. Raman sees polarizability moments. If you take a course in physical chemistry, and of course more detailed courses in spectroscopy in graduate studies, you will see the use of Raman spectroscopy. It's a very powerful technique, and it sees different stretches. Some IR stretches are invisible in Raman. Some Raman stretches are invisible in IR. Some are visible in both. It very much depends on the symmetries. But we can see things. You can see there the alkene or alkyne carbon-carbon triple bond. You can see that in the Raman, where you couldn't see it in the IR because it is polarizable, but it doesn't have a dipole moment. So key observations that I would take away from this particular section is that we need to have a dipole moment that is moving, a vibrating and changing dipole moment, in order to see something. So if it's symmetrical, so the dipole moment doesn't change, you're not going to see that stretch. And of course, I would point out that Raman spectroscopy can see that. And if you're interested in Raman spectroscopy or you come across it in undergraduate research, it is a fascinating technique and is very useful. But we're not covering it in this course. So those are some notes on some peaks that may be surprisingly invisible to you. So keep that in mind. Sometimes there's an alkyne in your molecule even though you don't see it. The degrees of unsaturation will reveal that to you. You'll be saying, I've got 2 degrees of unsaturation left over. I can't figure out where to go with them. I don't see an alkyne, but you know what? If I put it in a place where it is symmetrically or mostly symmetrically substituted, that would be consistent with the observations. So when you're thinking about von vibrations in IR spectroscopy, remember, draw that line at 3000. That's the first thing. To the right of it, those are your CH stretches. You'll usually have those. And to the left of it, is there an alkyne or alkene? You'll be able to spot them easily. If you've got a well-resolved spectrum, you should be able to spot them easily and quickly and go, I have an alkene. Now that alkene might be just a vinyl group, or it might be a phenyl group, or it might be a conjugated system. A little more analysis will determine that. Force constants are not always what we stated, 5 times 10 to the 5 dynes per centimeter. They are weaker with larger and floppier molecules. And of course, mass will change the frequency as well. We went to deuterium from hydrogen. We saw a great difference in frequency. Conjugation can change the bond order and therefore change the frequency of your bond. And hydrogen bonding, of course, will broaden OH peaks. You'll almost never see a sharp OH peak like I showed you in that first spectrum. It'll almost always be broad because most of the spectra you're going to do are going to be neat casts on a salt crystal. Key observations in the last slide there were that you need to have you need to have an asymmetrical changing dipole moment in order to see things in IR. And if you can't see them, you might be able to see them in Raman. So I hope you found that useful. In the next class, we're going to be basically looking at many spectra and building up our experience in what to look for identifying various functional groups. And really, it just all comes down to practice, practice, practice. So work along with me in the class and work along at home. Do every problem you can, examine all of the spectra in the book and treat them like problems and try and understand what each peak is. And try and build up a sort of a quick method, a quick little method that you come up with on your own how to identify IR spectrum. I always draw that line at 3000 first, look for alkenes, alkanes. Then I look for a carbonyl peak. Then I look for a CO peak. And then I look for other peaks. And pretty much for most small molecules, once you've got those first three things in there, you've got a lot of important functional groups that you've checked off. They're here or present or not there. And that can help you move on. And then I go to the NMR, which usually tells me everything I need to know anyway. So I hope you enjoyed this lecture, and we'll see you in class where we'll start doing some problems.